There are many reasons why you might want to take the limit as x goes to infinity or x goes to minus infinity, but what we're going to do right now is use it to find horizontal asymptotes of functions that have them. Basically, that's what you're doing when you're taking x goes to plus infinity. You're finding a horizontal asymptote as x goes to plus infinity, assuming it exists. And as x goes to minus infinity, you're looking for horizontal asymptotes on the left-hand side. So I want to go back to graphing functions. When we were graphing functions a few sections ago, we were graphing polynomials. We didn't know really how to handle horizontal asymptotes yet. Now we do. So we're going to start off with a function, say like f of x equals 1 over x squared minus 1, and we're going to do a lot of the things we did before, only this time there's going to be more parts to the question. So find intervals of increase and decrease. Hope you don't mind if I abbreviate things. INCR, DECR. I'm very short of space on this blackboard, so increase, decrease. Find and classify all critical points. This ought to look very familiar. C, find intervals where f is concave up and concave down. Find intervals where f is concave up and concave down. D, find points of inflection. E, find, let's do intercepts, x and y intercepts, where is it across the x and the y axis. F, find all horizontal and vertical asymptotes, assuming it has some. For instance, if we were just doing a polynomial, as long as it wasn't a straight line, you could just tell me, well, polynomial doesn't have any horizontal or vertical asymptotes, but rational functions can. Not all of them do, but they can. So intercepts, asymptotes, and let's get a good sketch. So really the only new part of this is finding the asymptotes. Everything else we've done before. And just like before, assuming hopefully you can see this and it's not off the edge of the camera, but parts A and B have to do with the first derivative, and parts C and D have to do with the second derivative. So let's go ahead and start taking derivatives. So f prime of x. Now, if we're smart here, we can save ourselves a considerable amount of work for taking the first derivative. We could go ahead and just use the quotient rule on that, but I think it's actually harder than it needs to be. Let's instead write this as x squared minus 1 to the negative 1. Taking something to the power of negative 1 is the same as 1 over it. So these two are exactly the same. If I write it like that, I can just go ahead and use a chain rule, and I think that's probably easier. So the derivative of something to the minus 1, we bring the minus 1 down. So I'll just put a minus sign there. I won't write minus 1, but you can write minus 1 if you like. Write the inside exactly as it is. The minus 1 becomes a minus 2. Then you have to multiply by the derivative of the inside part. The derivative of x squared minus 1 is 2x. Derivative of minus 1, of course, is 0. And I think I'm going to go ahead and write that back as a fraction. So I can write that as minus 2x all over x squared minus 1. I think that might be a little bit, oh, I forgot, the bottom is squared, because that's the minus 2 now. So let's go ahead and set up a sign chart for f prime. So I think I have space over here. So I'll put f prime next to my sign chart just so I can keep my f prime and my f double prime straight. I think that'll be enough. And let's ask ourselves where we put marks on this sign chart. Well, a fraction is 0 where the top is 0. Well, if 2x is equal to 0, x has to be 0. So this thing is 0 at x equals 0. Let's figure out where the bottom's equal to 0. If x squared minus 1 squared is 0, if something squared is 0, that something is 0. So basically, I just have to figure out where x squared minus 1 is equal to 0. And I can factor that, x minus 1, x plus 1. So this is x equals 1 or negative 1. So these are the two values, x equals negative 1 and x equals 1, where the denominator equals 0. So if the denominator equals 0 there, then we know that at x equals minus 1 and x equals 1, we have to put some marks. We can't put a 0 because the fraction isn't 0 there. It's undefined. So use another symbol. I like to use U. If you want to put a little infinity or another symbol, feel free. Just make sure it's not a 0. We ran into this problem earlier when we were doing sign charts, and it's just as important right now. So we can see that this thing, we've taken the real line and chopped it up into 1, 2, 3, 4 parts. Pick a value in each part. Let me pick, say, f prime. We're going to plug it into f prime. Everything about the first derivative sign chart goes into f prime. So a value to the left of negative 1, how about negative 2? So if I plug negative 2 in there, I end up with negative 2 times negative 2 all over negative 2 squared minus 1 all squared. Now the top comes out negative. There's another minus in front of that, so that makes it positive, and the bottom's always going to be positive because it's a perfect square. So it's positive divided by a positive altogether. It's plus over here. And we could plug in more points. I'm just going to go ahead and put them in for you. Minus, plus, minus. So this thing is going uphill, downhill, uphill, downhill. So in part A, we're being asked about intervals of increase and decrease, and I think we've got it now. So it's increasing from negative infinity to negative 1, and also from 0 to 1. And it is decreasing from negative 1 to 0, and also from 1 to infinity. We can read that right off the picture. I think we're also in a position to answer part B now. Find and classify all critical points. Now you have to be a little bit careful here. You might be looking at your picture and say, there are 3 critical points. There are 3 places where the derivative either equals 0 or it doesn't exist. But at 2 of them, the original function is not even defined. So x equals minus 1 and x equals 1 are not critical points because the original function isn't defined at any of those. If you plug x equals 1 into the original function, you get 1 over 1 squared minus 1. You get 1 over 0. That's garbage. It's not defined there, nor is it defined at x equals minus 1. So we really only have 1 critical point, and that's at x equals 0. And if you take a look at x equals 0, you can see we go down, we go up. It's a relative min. Okay, so we're as far as parts A and B. We know for C and D, we need to take the second derivative. I'm going to recopy my first derivative. Now let's see, I'm just going to squeeze it in up here. So f prime of x equals minus 2x all over x squared minus 1 all squared. Now we have to take the second derivative to answer C and D. Now I'm going to warn you in advance, the algebra behind this is not trivial. It's not hard, it's just tedious. So this time I think by trying to write it as like this, we won't actually save ourselves any work. If we leave the first derivative like this, we're going to need the quotient rule. If we try to write it like this, since we're going to have a 2x, we'll need the product rule and the chain rule. You can do it however you want. I'm going to leave it like this and use the quotient rule. So here we go. F double prime of x, we're going to take the derivative of this now. Here's that minus sign. I'm just going to write the minus sign down. Long fraction. Derivative of the top, that's easy. Derivative of 2x is just 2. Write the bottom exactly as it is. X squared minus 1 squared. Minus the top exactly as it is, that's 2x, times the derivative of the bottom, derivative of x squared minus 1 squared, chain rule. So 2, the 2 comes down, we write the x squared minus 1. The 2 becomes a 1, I won't write it. And now we multiply by the derivative of the inside, which is just 2x. All over the bottom squared. X squared minus 1 squared is x squared minus 1 to the 4th power. We're eventually going to have to figure out where that thing is positive and negative and 0 and undefined. Right now it looks miserable. So let's try to do a little bit of simplification on the top before we do any serious work. See if we can write this thing a little bit more simply. Now, look, we really have two terms on the top. Terms are made up of these individual factors that are multiplied together, and we have this one and this one, they're connected by a minus sign. Oops, forgot my minus sign out front. Don't want to do that. See, the major disadvantage of this format is I don't have you here to tell me when I make a mistake. So each of these two terms has an x squared minus 1 in it. This one has 2 of them. So I'm going to factor out that x squared minus 1 of them. X squared minus 1. Now I'm going to open square brackets. I factored an x squared minus 1 out of this first term, so I still have my 2, and I still have one of the x squared minus 1s. X squared minus 1 is still there. In this second term, I've completely pulled out that x squared minus 1. It's right there. It's out in front now. So what I'm left with is this 2x, another 2x. So 2x times 2x is 4x squared, times 2 is 8x squared, so minus 8x squared. And I have an x squared minus 1 to the 4th power on the bottom still. Now looking back at that, we have an x squared minus 1 on the top and an x squared minus 1 to the 4th power on the bottom. We can cancel this with one of these, making that a 3. Now we have an x squared minus 1 cubed on the bottom. And the top is starting to look better. Not great, but better. So minus 2 times x squared is 2x squared. 2 times minus 1 is minus 2. And then we have a minus 8. All over x squared minus 1 cubed. Oops. And 2x squared minus 8x squared is minus 6x squared, so minus 6x squared minus 2 all over, so minus 6x squared minus 2, hopefully that's visible, all over that x squared minus 1 cubed. And I'm going to bring that minus sign in to distribute on the top. So this will just be 6x squared plus 2 all over x squared minus 1 cubed. 6x squared plus 2 all over x squared minus 1 all cubed, in case I squeezed it in too small and you can't really read it. All right, let's go ahead and put our sign chart in for the second derivative. Remember, this is a sign chart for the second derivative. Don't put up and down arrows here. Up and down, the second derivative doesn't tell you where you're going uphill and where you're going downhill. It tells you about concavity. So 6x squared plus 2, let's ask ourselves where the top is equal to 0. Well, 6x squared is always at least as big as 0. And when you add 2 to it, it's always at least as big as 2. So the top is never 0. This thing has no zeros. But it is undefined everywhere the bottom is equal to 0, and the bottom is just x squared minus 1 cubed. Well, if x squared minus 1 cubed is equal to 0, then x squared minus 1 is equal to 0. So just like in the first one, this thing is undefined at -1 and 1. It's the same computation. If we set x squared minus 1 cubed equal to 0, then your next line is x squared minus 1 is equal to 0, and we already solved that. So we've just broken the real line up into 1, 2, 3 bits. And if you go ahead and plug numbers in, if we plug -2 in, let's see, we have positive, it's positive over here. This time you're plugging into the second derivative. When you're doing a second derivative sign chart, you plug everything into the second derivative. Wait a second. I think I made a mistake somewhere. I did. I made a mistake way back in the first derivative. Okay, let's go back to the first derivative. I plugged in points and I wasn't being very careful about the whole thing. So if I plugged in -2 and I did this computation, and I did in fact end up with a positive number, but I jumped to conclusions when I got to the -1, and I told you never to do that, and then I did it, so I apologize. As it turns out, in the first derivative, it's still positive over here. That's still going uphill. And when x is greater than 0, now it's negative. And if x is greater than 1, it's still negative over here. So it's up, up, down, down. I apologize for that. So where I have it increasing and decreasing, I have made a mistake. It's increasing from -infinity to -1. We can see that, but it's also increasing from -1 to 0. And it's decreasing from 0 to 1, and also from 1 to infinity. So I switch these two in the middle, and as I said, I don't have you here to correct me when I'm wrong, unfortunately. Hopefully some of you noticed that and didn't take my word for it, but if you did, it's certainly not your fault, it's mine. And we can still see that we only have one relative max or min, but at x equals 0, it's not a relative min, it's actually a relative max. We can see we're going uphill and then downhill. So relative max. All right, let's try again. So down here, if I plug in x equals -2, so f double prime of -2 is going to be 6 times -2 squared plus 2. The top we know is going to be positive. -2 squared minus 1 cubed. That's going to be 3 cubed. The bottom is going to be positive. It's definitely plus here. And when we go through the -1, it does become negative, and then it becomes positive again over here. Okay, so concave up, concave down, concave up. So for those of you that are really interested, you might look at what it was about the second derivative that made me realize that I had made a mistake in the first derivative. All right, so we can answer C and D now. C, where is it concave up and concave down? Well, it's concave up wherever we have these plus signs. So it's concave up from -infinity to -1, and concave down from, also from 1 to infinity. Concave down from -1 to 1. And we can see, do you see any points of inflection at all? So remember, to be a point of inflection, the curve has to be differentiable and the concavity has to change. Now it looks like the concavity changes there. It absolutely does change, but the curve is not differentiable at -1. It's not even defined. Same at 1. Even though the concavity changes there, the curve is not differentiable there. Remember, differentiable means smooth, and if it's not defined there, it certainly can't be smooth. So there are no points of inflection, even though it looks like there are at first glance. We'll have a better idea of what happens at x equals -1 and x equals 1 after we do the other parts of this question. So I am going to get rid of all this work down here. Again, I guess the advantage of doing things in this format is you can always pause the video. All right, find intercepts. So for your x-intercepts, you know what to do. You set y equal to 0. So y is just equal to f of x. So if 1 over x squared minus 1 equals 0, a fraction equals 0 where the tops equals 0. Well, 1 never equals 0. So this thing has no solutions. So there are no x-intercepts. And for your y-intercepts, we'll set x equal to 0. That we can do. So y equals 1 over 0 squared minus 1. That's 1 over -1, which is -1. So y-intercept, y equals -1. That's part E. Now let's do F. This is the new part. So hopefully you have this all copied down. I'm going to erase it. Let's do our vertical intercepts first. So the original function, f of x, if we factor the denominator, 1 over x minus 1 times x plus 1, we know that every place where the denominator equals 0, we either have a hole in the curve or a vertical asymptote. In this case, you can't cancel the x minus 1 with anything on the top. So this leads to a vertical asymptote, and you can't cancel the x plus 1 with anything on the top. The only time it's a hole in the curve is if you can cancel a factor in the bottom with a factor on the top. So we have a vertical asymptote at x equals 1 and x equals -1. So vertical asymptotes at x equals 1 and x equals -1. You can think of x equals 1 as a mark on the x-axis, but you can also think of it as an entire vertical line. and the horizontal asymptote. This is the new part. So what we're going to do here is we're going to take the limit as x goes to plus infinity or minus infinity. It doesn't matter. Rational functions, if they have a horizontal asymptote on the right, they have the same horizontal asymptote on the left. So we'll take the limit as x goes to, say, plus infinity of 1 over x squared minus 1. And we can multiply the top and the bottom by 1 over x squared, just like we did in the previous section, in the previous video. And we're left with the limit as x goes to plus infinity of 1 over x squared times, x squared times 1 over x squared is 1, minus 1 times 1 over x squared is minus 1 over x squared. And again, that looks worse, but it's actually better because as x gets very big and positive, or very big and negative, that goes to 0, that goes to 0. What we have is 0 over 1 minus 0, 0 over 1 is 0. So we have a horizontal asymptote at y equals 0. I think we have just about enough information to be able to graph this thing now. So let's make a good sketch. Okay, so I am going to put my vertical axis right underneath the 0 of my two sign charts. I'm going to put my horizontal axis. I'm going to try to make all the points line up. Minus 2, minus 1, 1, 2. Here's my x-axis. Here's my y-axis. I have some interesting points. I have an interesting point at x equals 0. At x equals 0, I cross the y-axis at, where am I? At negative 1. So at x equals 0, I cross the y-axis at negative 1. I know the curve goes through that point. Let's sketch in our asymptotes. I have a vertical asymptote at x equals minus 1. I have a vertical asymptote at x equals 1. And I have a horizontal asymptote. I have no idea whether or not that's visible. At y equals 0. All right. Even though I have only one point sketched on this thing, looking at my first and second derivative, or equivalently all this information that we have over here, we can sketch this curve. So from negative infinity to negative 1, we are increasing, concave up, increasing in a valley. We approach this line asymptotically, and we approach that line asymptotically. There's really only one choice for how this thing could look. Increasing in the valley, approaching this horizontal line and this vertical line, it has to look like this. It gets closer and closer to those two lines. From negative 1 to 0, we're going up. We're increasing, this time on a hill. And at x equals 0, it's horizontal. So increasing, it gets level here, increasing on a hill, and it approaches this line asymptotically. So the curve looks like this. Increasing on a hill, it approaches this line, levels out right there. From 0 to 1, we are now decreasing. We're going downhill, still on a hill. Has to look like this. And from 1 to infinity, we're going downhill, in a valley, downhill, concave up. It approaches these two lines asymptotically. It has to look like this. With only one point, we were able to sketch this picture.